So we're going to talk about this a lot more, but the reason I wanted to bring it up is because of the demonstrations. And so this particular demonstration, the idea is, so this is a pendulum. If I took away that bar, then it would just swing back and forth. But what we talked about last lecture was this idea that work, which is the integral of the force over distance, it gives you a change in kinetic energy. So when we look at the pendulum, you can think about it as it goes back and forth as this. The total energy is constant, but there's kinetic energy being turned into potential energy and vice versa. And so when it's up at the maximum, then if I just let this go, at the moment I let it go, the velocity is 0, but it's accelerating as it goes down. And then when it reaches the bottom, it's at its maximum kinetic energy, so maximum speed at the bottom. But the potential energy, so the whole thing is driven by gravity. And so the potential energy is, if we define it like that, where it's the integral of the force, the potential energy only depends on height. And so if I drop it here, it'll come back up to the same height. So the thing that happens here is when it reaches the center, the pendulum is now different length, but it's still going to come back to the same height because it has the same speed at the bottom, and it'll reach the same amount once total energy is conserved. So that's the point of this experiment. So if you can see this line, when I drop it, it should come back on the other side. It reached exactly the same height as I started it off on. You can see, and you can just let it go, even though the length of the pendulum is changing. The maximum height reached is the same on both sides. And that's got to do with the fact that the total energy is conserved and kinetic energy is being converted back and forth into potential energy. So, yeah. So last week we talked a lot about friction. So I have a few, move these over because I think the camera here. So we have some blocks and a scale here. And the point of the scale is to hold it, and then you can pull this, and it lets you measure the force here. So I can take a block. So let's take this one, and you hook it on. And now the idea is I can pull it. So we talked about static friction. So if I pull it and the block is not moving, you can see the force goes up. And then at some point, the block starts to move, but you can kind of see that the maximum it reaches is here like 4. And then while I'm pulling it, it's around 3. So the 4 would have been the coefficient of static friction. And the 3 is the coefficient of kinetic friction. And often, so with static friction, the friction force is not moving, so it's exactly balancing whatever you're pulling here until it reaches some maximum value. And the kinetic friction is just the amount that it's pulling back. So if I pull it at a constant rate, it'll exactly balance what I'm pulling. So, right, so that actually gives you force as a function of the friction force. When it was static, it went up, and so it was exactly balancing until it what I was pulling until it reaches the maximum, then it drops a little bit for the kinetic. So the kinetic coefficient of friction is usually a little bit lower. So, so let's go back and do this again. So I did this. One of the amazing things about friction is it just depends on the normal force. And so, so for this block, this is the Coulomb law of friction. So for this block, the normal force doesn't, I can put it this way, and it wouldn't have, the Coulomb law of friction would tell me that it wouldn't change. So even though there's a completely different surface area there, and there's a completely different, the amount of states interacting between the table and the block is now much larger. It's the Coulomb law tells me that it should be the same, and it's approximately right. So if you look at this, I pull it till it starts to slide, and that's about 4. It's a little bit higher. And then when it slides, it's a little bit lower. It's like 3. So it is about right. So what, I mean, you were seeing it stick slip, so that's a whole other set of friction. And stick slip is uneven behavior that you can see in frictional systems. Actually, so there's certain things that depend on stick slip motions, like braking or violin strings. If you look at when people play violins, you have to have the string constantly slipping from the friction of the bow. And the bow, they put all this rosin on it to make it more friction. So violin doesn't work unless you have this stick slip that actually goes in with the modes of oscillation of the string. So, so this was just a block on a table. Let's try a block with a rougher surface. So this is sandpaper now, and we would expect the friction force to be a little bit higher. So this is the pull, and this is, let's see if I can just, that won't let me do that. Okay, here we go. Let's try it this way. So this should be a little bit more of this friction. Let's see if it is. Yeah, maybe it's not really that different. I would have thought it'd be more. Still about the same. In any case, then there's tape on it. So let's see if that's different. Yeah, that is quite a difference. See, I can pull it and the tape, and that's more down that way too. So the tape is quite a bit slipperier than the sandpaper. So the other thing with friction is it's not supposed to care about how much mass there is, the friction coefficient. So, but when I pull it, it should. So, I mean, I should see the difference. Yes, so it should be twice as much. And before I had like 3 or 4. Wow, it went up to 10. What did I put on the bottom here? That's just the wood, huh? So it should have been exactly twice because the mass is about twice. It's a little bit more than twice. It went up to like 11 there. Surprising. Okay, so then the other thing you can do is you can take a block like this, and the idea is the friction shouldn't depend on whether I'm pulling it this way or that way. It has the same friction coefficient. So this is, again, it's a little bit counterintuitive. Coulomb law, the Coulomb laws of friction are really independent of all the microphysics. Because when you look at this, you'd think it would make a difference if you pulled it this way versus that way, right? So, I mean, intuitively, actually, you can feel it. It doesn't really make much difference, but we can try and see, does the meter show that it doesn't make a difference? So let's give it a try. Yeah, so pull it along the edge. And the coefficient of static friction is like it was before. It was at 4. And now let's try the other side. And this way. And again, the coefficient of static friction is again like 4, and then when I pull it at a constant rate, it's like 3. So that at least really did show what we were supposed to see. So the other thing we have is, so rolling is a subtle, somewhat subtle situation. So when you pull something with wheels, you intuitively know there's like a lot less friction. And if I pull it with the wheels flipping, it's hard to pull. So when we'll talk about what is this what's going on here is the surface is always in contact, and so it's what's called a rolling without slipping constraint. But it does require friction to set up. So yeah, so if there were no friction, you could pull it and the wheel wouldn't start turning. So so the rolling without friction constraint, we usually put it on as if it's a frictionless situation, but it wouldn't actually occur without some friction. So there's a little bit of subtlety in it, which we usually ignore actually when we talk about rolling without slipping constraint. So this is, in this situation, that's why it's called a constraint, and some constraints don't take any energy out of the system. This one, you assume that no energy is removed from the system. In reality, there has to be a little bit of energy removed, and that gets important for things like tires. So you do actually lose quite a bit of energy through tires, even though they're rolling, right? Rolling without slipping, and that rolling without slipping constraint minimizes friction, doesn't do away with it altogether. Okay, so let me now go to the other side. I'm supposed to just turn this over. See if that works. Does that work? Yeah, it looks kind of okay. So, so we have a vacuum pump here. And this thing, before lecture started, you might have heard us turn it on. And there's a buzzer inside, which you can barely hear. And then, and that it's hard to hear because there's not much air inside the barrel here, or inside this bell jar. And actually, you know, I can try and pull it up. It won't come up. But if I let the air in, so let's see if we let the air in. It gets louder. And it gets annoyingly louder. So what's the point of this experiment? And now it's all out. It's very loud. So what's the point of this experiment? This experiment is to try and show you that sound waves are, you need air for sound waves to exist. And that air is actually this thing. It's in, you know, so we don't live in where there's nothing. We actually live in this hydrodynamic aerodynamic environment. One of the things it does is it transmits sound. So air also has pressure, and so that's what this is supposed to show. So so if you pull air out, then the air from the outside pushes on this, and then you can't pull it apart. And so let's see if I can turn this on. There we go. Okay, so then I turned it off. So it should be holding a vacuum now. And now I can just hold this and nothing, it doesn't come apart because I've sucked the air out. So when you think there's a vacuum inside, what's really happening is the air on the outside is pushing on this. And so it's actually under pressure, but because there's less inside, you can't just pull it apart. So I think I can take this off now, yeah. And I can now let the air back in. You can feel it. And then it should just come apart again. So air pressure is a real thing, and that's what this shows you. So later on in the term, we'll talk about PdV work, which is how much work can be done by a gas. And so pressure is the force per unit area. So when you have something that fills space, that you describe the force that it can exert in that way. So and this is, it's kind of hard to tell, but with the nozzle, for example, I could think about how much pressure is being exerted on on the cross-sectional area of the nozzle by the gas, and that would be dependent upon the pressure. And then if you want to say how much work, like if I were going to use air pressure to raise something against gravity or to accelerate something, I can calculate that with the distance traveled, which would then be related to the change in volume. And so that's where we get this idea of PVD work that gas can do. And then so things like heat engines and air conditioners and things like that all depend on converting work from heat energy and back and forth in work. So we'll talk about that at the end of the semester. So the last experiment we have is another friction experiment. So this is this one where we were talking about last time we talked about this inclined plane. And so if you put a block, so this block we have a sandpaper side and a smooth side, and I can put the block on here, and then I can slowly raise the angle. And then at some point, right now, static friction is opposed, so gravity has the component that way. And if I raise the angle enough, then I overcome the coefficient of static friction and it starts to slide. And so I can measure the coefficient of static friction from the critical angle where it starts to slide. And that was around 25 here. And then if I change the surface, so now it's the sandpaper, it should be rougher, it should have a higher coefficient of friction. And it's a little bit sticky here, but there. So it was a little bit higher, around 32 for that. So that illustrates that. And last time, right at the end of lecture, we calculated the angle, and it was the tangent of that critical angle is equal to the coefficient of static friction. So, and the way if you remember how we calculated that, we calculated by figuring out the component of gravity in the vertical direction, which is the normal force, and then the friction force, which is in the tangential direction, is now equal to the normal force times the coefficient of static friction. And we need that to be overcome by the component of the gravitational force along the surface. So that's why we get both a sine and a cosine in the relationship. Okay, so that ends our demo. Next week we'll get the bowling ball, because the bowling ball was hard to set up. So let's now go to the Hoyt board. Yeah, so do we have any questions about the demonstration? Yeah, okay, good. Everybody's good. So there is I think not next, so next week you guys have the lab report due. The week after the online lab is friction on friction, actually. So you measure the coefficient of friction for different masses and different surfaces. So the on-campus lab, I don't remember what it is actually, gravity or something. I don't remember what the second one is for that. Yeah, I always find the Coulomb law of friction really mysterious. Like all the physics is somehow irrelevant. Kind of weird. Okay, so let's go to potential energy. So, so let's remind you guys what we did last time. So we wrote the work is an integral of force times distance. So I'm going to, instead of using Z, which I did for the pendulum thing, we'll just have that for that. And integrating it over a distance. So work is force times distance, but then if you have a varying force, then you need to integrate out this little piece. So here we have some x1 and x2, and we have these little forces here. And we're integrating up the work. So, so this is a function of one variable, and I can say, well, can I find some other function such that du dx is equal to f? I'm going to put a minus sign here. So this is the same thing as I wrote here. So we want one dimension, you can always do this. In 3 dimensions, you can't do it. But whatever x of x is, I can always find some function such that that's true. So, then let's now use this fact so that I can rewrite this now. And I'll put that in there. Minus dx, and this I can integrate. It's pretty easy to integrate. So I get u of x2 and then there's this minus sign. And so this is equal to minus delta u across the path. So what this is saying is, by integrating this thing along the path, we're thinking about the work done along the path, and we have to add up all these little pieces. But if we describe it with a potential function, we don't need to worry about what happened along the path. We can just figure out what the potential energy was here and the potential energy there, and we would know the work done on the path. It just depends on the difference. So that means I could take another path and I would get the same work along the path. So any path gives me the same work. And I just calculated from this potential energy function. So that's kind of cool. So, so this is, I do this way. But what if I go first this way, and then I come back on this path? So this is a loop. And if I go this way, I get minus 2 minus ux1, and I go that way, I get the opposite sign. And so if I integrate around the whole path, so let's put them down. Well, let's just all erase there. Here. So if I integrate u around the loop, it's f on u. On a loop. In this case, in 1 dimension, I get 0. Just the opposite sign to go halfway and other way around. And I can move x2 wherever I want. Here. So you could move x2 there, or I can move it here. It doesn't really matter, because if everything just depends on the potential energy, we'll change along this path, and then I'll get the opposite sign going around. So this is telling you that, yeah, okay, so this is always true in 1 dimension for any force. So if it's not always true in 3 dimensions. And the reason for that, this is only true if we can find a function like this, the du dx equals to f. So work, I could have a force in general as a vector. So work is a vector times dx, which is a displacement vector. So when I draw these things, you can think about it in 2 dimensions. So once I'm in 2 dimensions, or 3, I can't always find a function such that the gradient, so this is now the gradient. What do I mean by this in 3 dimensions now, or 2 dimensions? How would I generalize that? So I can always write this dot product. This would now be a vector. So this has to be a vector also. And so what this would turn into would be this. these are now partial derivatives. Y, U, Z. So U is now a function of x, y, and z. And if I take a derivative of respect to x and a derivative with respect to y, then I get a vector, and that vector will equal minus the force. And so another way to write this is gradient of u. So that's what it turns into in 3D. But it's for any force, it's not necessarily possible to find a function that only depends on position that you can do this. If you can do this, then your force is called conservative. So if there is a function u of x now 3D such that, and I'll just use the gradient symbol. Then x is a conservative force. And that means if I integrate the work around the loop, I always get 0. And it also means that the work done between any 2 points only depends on the energy difference, the potential energy. So yeah, so conservative forces are nice. And a lot of the forces that we'll talk about will be conservative. So like gravitational vertical acceleration is a conservative force. And the gravitational force as a function of radiance, meaning, for a whole planet, that's a conservative force. And the spring force is a conservative force. An electrostatic force is a conservative force. Velocity-dependent forces are not conservative forces. And anything that has a lot of rotation in it, like you have a force that somehow gives you a spiral or something, that won't be conservative. So you can go around a loop and not get back. Yes, question?
Does that work the other way around? If that's the conservative force, then there's a function u of x such that it's gradient u equals negative x. Or is it a
yeah, this is the definition. So if you can give me this function, then it's conservative force. Yeah?
Wait, what does U stand for again?
U is the potential energy.
Oh.
Yeah. Yeah. U is the potential energy. Okay. So right. So last time we showed that if you exert a force on a point mass particle, or it doesn't have to be a point mass, just a mass like a block, that you get a change in kinetic energy. And now if I have a conservative force, that's also equal to minus the potential energy. So the work is equal to the change in kinetic energy is equal to minus potential energy. That means if I add the potential energy plus the kinetic energy, I get constant. So what we're finding here is for a massive object under a force, there's going to be a conservation law. The energy is going to be conserved, and energy is the sum of kinetic plus potential energy. You were headed on this? Conservation law, yeah. Okay, so let's talk about conservation of energy. So this is the back end. Almost got it all erased. Okay, so conservation of energy. So I'm going to do for non-relativistic particles, There is a generalization for relativistic particles. But we'll define the energy, the kinetic energy plus potential energy. So normally, you know, before we were starting with forces, and you assume you integrate the force to get the potential energy. So I'm just going to start with potential energy here. So we'll work with in one dimension for the moment. So U is a function of x, and the kinetic energy is 1/2 mv squared, and v is dx dt. So let's, what do I mean by conservation of energy? It means it's not going to change. And so that means d dt should be 0. But let's take the derivative of it. So take the derivative of this. Its mass will not going to change. So we have m v d dt. I take the time derivative of it. And I'll take the time derivative of this. So just have to use the chain rule. So this is going to be du dx times dx dt. That's just the chain rule. And dv dt times m is the force. So this is Vf. And du dx is minus the force. And dx dt is v. And so this is Vf, and that's Fv, and that's 0. It'll cancel to be 0. So I mean, you can show this, but really we knew we were going to get this because we had already shown that when you look at the work, when you look at the work, it's a change in kinetic energy. And so if I, you know, when I do EDT, I'm looking at the work over a small time. And so you can look at this, and this is F dot V, that's the power. And this is the change in kinetic energy. So it's equivalent to our previous statement that work was equal to the change in kinetic energy is coming out here. So there's nothing different about it. So we did this in one dimension. So now let's just generalize it to 3. We'll assume we have a conservative force so that there exists this function u. And this is dx squared plus dy squared plus dv squared. And when I take the derivative of this, I just get a dot in here. So it's v dot dv dt. And here I have the gradient of u dot v. So this I could write like this. I could put a vector down there, or I could write it as grad u. Same thing. And then this would turn into this dot product. So it works in 3D also, as long as you have a conservative force. So in 1D, we found that you could always find the potential for any position-dependent force. So right now we're doing position-dependent forces. Velocity-dependent forces aren't conservative. Okay. So, right. So one of the things that you have with conservative forces, if you integrate around a loop, means you come back to the original position. You'll never do any change in energy. So the work done around the loop is going to be 0. So let's find a counterexample to that. So let's do I'm going to do a velocity-dependent force. Just to show you that when you go around a loop, you don't get 0. So, so let's do that. So this is this was the damping. This is a damping force, and it's a velocity-dependent force. And if I do, now let's go around some trajectory. Times dx, and it's convenient So this is minus alpha v, and I can turn dx into dx dt, dt, and then this is going to be minus alpha v squared dt. And I can have this also be all vectors if you want. There's nothing necessarily here that, so work is a scalar, but there's nothing in any of these equations that didn't let me turn it into a vector equation. So now look at this thing. So this is work. I could go around the loop and come right back in position to where I started. But it's the integral of v squared minus v squared times dt. So this is always negative, this thing. So that means the work done around any loop is always less than 0. And that's maybe not surprising because this velocity-dependent force is always going to take energy away from your system. And so last time we actually solved the position as a function of time and velocity as a function of time for a particle that is only affected by this force, and you just saw that velocity drops to 0 and the position kind of coasts to a slightly different position. So it's not surprising that you're losing this. The work is negative is equivalent to saying we're losing kinetic energy. So this is not a conservative force. Okay, so I mentioned we're going to generalize for a relativistic setting. So let's take this off. So energy. So this was what we had for a non-relativistic setting. For a relativistic setting, we changed our definition of energy to be consistent with our relativistic definition for momentum and to maintain this thing called the energy principle, which is telling you that the gradient of U is equal to dP dt. So what we do here for a relativistic setting, so this is the non-relativistic. We had the relativistic energy we added the potential. And relativistic definition of energy was that. So we would say you have a particle that's now the total energy, potential energy plus the relativistic energy. And in the limit of low velocities, gamma goes to 1 plus the kinetic energy, right? So remember the E minus mc squared. So E minus the rest energy is equal to the potential energy. So with a non-relativistic particle, I can just add a constant and it won't affect the dynamics at all. So remember, force is minus d dx or the gradient. But if I add a constant to it, the force doesn't change. So, so you can always add a constant to your potential energy, and it's not going to affect the dynamics at all. So the 0 point, though, for energy for relativistic particles is actually kind of important. And so in the non-relativistic case, we often are adding constants. In the relativistic case, we're often trying to be a little bit more careful because rest energy has a meaning in the the relativistic setting. So, so for example, particles can annihilate and give you different mass particles. Yeah, question?
So I know like E equals gamma mc squared and everything, are we supposed to understand how that happens? Because I know that's a fact, but
Right.
I don't
So
know why.
yeah. So that's super annoying, right? Because in this class, I'm not actually we're not actually doing special relativity, but we are giving you relativistic definitions for energy and momentum. So that's kind of a confusing thing. So we could do that. So I thought about that last year when I was teaching this class. Should we just start do special relativity at the end of the class, and then we would derive it with, doing Lorentz transformations and all that, and then calculus space and metrics. So that would go against our curriculum, which is set up by not just me. So I had, I could just annoy my colleagues, which is tempting to do, but but officially and planned is that you will cover special relativity in a lot of detail next term, I think. And then you will go through, Lorentz contraction and time dilation and all the paradox things, the spacecraft, and then you will show again why these make more sense. And you'll also do this in the context of electricity and magnetism, where you'll see that Maxwell's equations are really relativistically invariant. They're consistent with special relativity. So that's a nice, I guess that's a nice way to introduce it. So rather than do special relativity in this class, we're doing a pretty serious introduction to statistical mechanics. So we are going to derive some stuff from first principles, but not this. I thought about it last year as well. Yeah, because it is annoying, right? It looks like we're kind of stating it without proving it. Yeah. But that doesn't mean you don't have to read about it. So you can look at, there's some nice introductions to special relativity that talk about how it's motivated. So what motivates it is this principle that your lab experiments shouldn't depend on what speed your lab is moving in, and that the speed of light is the same in all reference rates. And so if you take those two assumptions, you should find that the only transformations that make that possible change your definition, the way you think about space-time, and then you get this gamma factor out of the transformation. So you have to understand that assumption and then write down transformations that make that possible, and you will get special relativity. In hindsight, it's probably easy, right? But probably not easy to find it in the first place. Okay, so now we have lots of examples of using potential energy. So I guess that's what I'm going to do next. So I think I'll just erase this and do the first example. We're going to use the board here. Okay, so yeah, okay, so let's look at the velocity from a potential energy system. So we have a difference. So we have a particle, and it has mass m, and it has initial position and it has a initial velocity. Sorry, V1, V0. Jumping ahead here. Okay, initial velocity V0. And now we're going to move it. So let's move it. Or it's not like we're moving it, we're letting it move under the force that it's under. And we're going to move it to this new position, x1. So the particle is moved. The question is now, what's the velocity? So the particle has a force. The particle is under a force with potential energy u. So we're also given this function. So our goal is to find the new velocity, which we solve for that. So this problem, we use the fact that energy is conserved. So energy is the kinetic energy plus potential energy. And it's not going to change as the particle moves from x1 to x2. So I can figure out what the initial energy is. Let u 0, this is the first initial position, so that's 1 mv0 squared plus u of x1, or x0, right? So that's the initial energy, and that should be equal to the final energy. The energy is conserved. So we'll just set it equal to the final energy. And now we can solve for V1. So 1 V1 squared is equal to now multiply both sides by divide both sides by 1/2 m. 2 over m. 0. And then V1 is just the square root of that. Okay, so that shows you how to get the final kinetic energy from the initial one. So there are lots of examples now. So that's like if I drop a ball or drop something and I want to know, so I'm letting it fall from one position to another. If I started at rest, I'll know the initial velocity. Then I should know the final velocity when it reaches some other position. So let's now apply this. We'll do an example of dropping a block, and we'll be able to compute the final velocity just from the potential energy difference. So instead of having, so this saves you some time, right? The idea is I don't have to solve the equations of motion and find position as a function of time anymore. All I need to do is figure out what the beginning and the end is, convert it into an energy problem, and solve it, and I'll know the final velocity. So that's the idea. It saves you some conservation of energy. Okay, so that's the next example. We're going to talk about gravitational acceleration. So gravitational and this will be on the surface. So gravitational acceleration is F minus mg. So this is for a particle or a block of mass m, and it's down. So if I have a coordinate system x, y, and z, it's in the z direction. So this is the unit vector pointing up. So can I find a potential energy function such that so d, yeah, we can. So du dx, f doesn't have any x direction component. So that's 0. So u doesn't depend on x. That's easy. Du dy likewise is equal to 0. So du dz is going to equal minus mg, right? So that I can iterate this, and there's a minus sign here. There's a minus sign, just the minus the gradient of u is equal to the force. So u is mgz, so I can integrate this on both sides plus a constant. So potential energy is bigger as you go higher. So this is the answer. We found the potential energy function for gravitational acceleration on the surface of the Earth. So let's now do a couple of problems. So supposing I have a block and I move it from the tabletop here where z equals 0 to z equals 8. So I'm going to pull it up or raise it. So I can ask, what's the work done by gravity to do that? Gravity is exerting a force down, but force times distance. So gravity is this way, my displacement is that way. And so we can say work distance. In this case, we could actually integrate it, but this is a constant acceleration. So gravity is in that direction, displacement is in this direction. So they're in the opposite direction. So it's minus sign mgh. Okay, so the work done by gravity is negative, and that is kind of the same thing as saying you're getting to a higher potential energy. So I'm trying to get you used. The work here has the same size but opposite sign. Work done by gravity, same size but opposite sign as the potential energy. Is this getting used to the idea of time of work? Okay, so now let's turn the problem around, and we'll say I'm going to start the block here, and I'm going to let it fall down to the down. So starting at equalization, I'm going to let it fall to equal 0. And I want to know what the velocity is when it hits at this location. So let's do that problem. You guys you probably know this. Okay, so we're starting with block at z equals 8. That's mass m. We're going to start it at b equals 0. And we want to know what the velocity is when it hits the 4 at z equals 0. So energy is constant. And the initial energy, so let's take potential energy. mg. The initial energy is kinetic energy plus potential energy. So if the velocity initially is 0, the initial energy is mgh. And then that's constant. The final energy should be the same thing as the initial energy, but now it's the kinetic energy plus the potential energy at the new position. So this is going to be the velocity and when it hits down here, but the potential energy mg z is 0, so there's no contribution. So this I can solve for v, and the m's cancel out, m's and v 2GH, right? Oh, this word. And that's the answer. So we didn't have to solve the equation of motion. So that was maybe a little bit faster. So there's lots of problems like this. Like you can let ball roll downhill, you can like start with a spring and hit it, and then look how far does it go, things like that. Bunch of problems where that's the whole idea. You save yourself solving the equations of motion by using the fact that energy, like that energy is a conserved quantity, and then you can compute it with the sum of kinetic energy. So not all our forces are conservative, so let's do a problem with that. It's not a conservative quantity. So how about friction? So yeah, so that our previous problem we raised something. The work done by gravity was negative because we're the opposite of the change in the potential energy. So suppose we have friction. So let's do a work done by friction. The point of thinking about this is sometimes you have problems where you have both potential energy, you also have energy loss mechanisms. And if you start off with a certain amount of energy, you could be losing energy into friction. So there will be work done by friction, which takes away energy. And then you can think of that as a negative work. And then whatever is left might go into something else, like spring, pressing, or something like that. So we have various examples like that. So, so supposing we have a mass M, and it's on a horizontal surface, and we're going to push it horizontally some distance d, and it's under the force of mg, and the kinetic coefficient of friction is that. So what's the work done by friction? So if you remember the friction force, if I move it, it's the relevant one is the kinetic coefficient of friction. So static coefficient of friction is irrelevant because there's no displacement. You pull it, but nothing's moving. So there's no work. But with the kinetic one, it's moving, so there is work. So the friction force, horizontal friction force, is the kinetic coefficient of friction times the normal force, which is mg. And then the work is, we're integrate that. So this is horizontal, so we have a friction. So if it's moving this way, so D is moved that way. The friction coefficient, the friction force is always in the opposite direction of which direction it's moving. So the work, which is this times the displacement, is going to be negative. And so that's the answer. It's a minus, which means it's removing energy. So we could think of this block, if you started this block at some velocity and it coasted d until it stopped, the kinetic energy would be 1/2 mv squared. That would be equal to this. So you could figure out how far it goes to stop. You could also solve that this way. Yeah, question?
So for total energy, would that just be the kinetic energy minus the work done by friction?
Okay, so total energy is conserved if you have conservative force. In this case, we have a non-conservative force. There's no potential energy in the problem. But if we started the block moving, we could say how far would it get? And we would get this far. So this is the initial kinetic energy. This is how far it would get because we need friction force to get rid of all the kinetic energy. Does that make sense? Yeah. So work is still work. We only deal with constant energies if we have potential force. So you just have to remember that. There's nothing wrong with work. Work is always work, no matter whether you're conservative or not. You don't have conservative forces. And you can still keep track of energy, even if you don't have conservative forces, because they just take energy out of your system, typically. Okay, so that was an example. Just a little bit of the subtlety of that. Okay, see, we're just going to do a lot of different examples. What does potential energy look like? Or what does work look like? So, potential energy in a spring. So here we have a spring, mass M, spring constant K. So this distance was a displacement from the rest position. So I guess let's call this X. This is the rest position. For a spring, and the force X. So it was in the opposite direction of X, which makes sense if you're pulling X. If the mass is pulled, then the force is backwards. If the mass is pushed this way. So this is a one-dimensional force. So we can do this X, and we can integrate it. And there's a minus sign, right? So use minus, so I have a minus sign, so let's get rid of the minus sign. And that's going to be K X squared over 2 plus a constant, which we don't care about. So use X for the spring. That's nice and simple. Yeah, so now it's actually kind of nice to write down the total energy for spring or harmonic motion. That's the kinetic energy plus the potential energy. And this is conserved, right? So, so this is conserved now. So that maybe a little bit easier to see that if I go into phase space, the trajectories are ellipses. Because this is V and so if V goes to 0, then X is the biggest we can get, and you have to stay on the ellipse in order to keep energy constant. So that's the harmonic oscillator with the potential energy term in it. Okay, so that was potential energy in the spring. Now we'll move on to gravitational potential energy. But before we did gravity with just the vertical component, now we'll do it with the radial version. Oh, look, I have gravitational potential energy. I can just keep that there. Right. So, so here now, instead of being on the surface of the Earth, we have some planet, and we can take things. Let's say we have some satellite starting here, and then maybe a little so energy is going to be conserved. So kinetic energy plus potential energy is going to be conserved. So if I know the velocity here and the potential energy here, and I want to know what's the new velocity, I can figure it out just based on doing exactly what we did before, where energy constant, potential, you know the potential energies for both of those positions, you know the kinetic energy in one of them, and you can figure out the kinetic energy in the other. So, but in order to figure out what we need to do is have to compute gravitational potential energy for this gravitational force. And we wrote down the force law before. So, so if this had mass big M, and I have a particle here, little mass little m, then the gravitational force looks like this. And so I'm going to make R be from the center of the big mass, and we'll assume that little m is really small. So little m. That way I don't have to worry about the center of mass being something different. And it's an attractive force, so the force is that way. Like that. And R hat is this radial vector that's coming from the origin to the position that we're at. So, so this is now a force in 3 dimensions, but we know that the force is radial, so the potential is only going to depend on the radius. So we could work in cylindrical coordinates, for example, or we could work in spherical coordinates, and but either one you can just write down the gradient. But we know that the force is only radial, so the potential will be able to write as a radial function, because otherwise we would, if the force had any tangential components, then the potential would depend on the angles. But it doesn't have any tangential components. So so U of R, so U is going to be a function of R. And so we just need to integrate this. Squared dr, and then there's a minus, we get minus sign, because grad U is minus F. And so this is E M of R, and a minus sign. If I take the derivative of this, I get minus G of M over R squared. Plus. So usually the constant we ignore in this setting. So for gravity, like that. And you'll see people often forget this little math here. So that's because kinetic energy depends on M, and potential energy depends on M. And so total energy, often people will write total energy per unit mass, because it drops, it's on both terms exactly the same way. So you'll see people being sloppy with what they call potential energy per unit mass. So now we can answer our question, like if we started here and then the orbit moved it there, what would be the change in the kinetic energy? Well, the change in the kinetic energy is going to be the difference in the potential energy. Yes?
So is the exponent for U of R, what's the exponent to R to 0?
What, did I write something funny? That's just a funny curly R.
Oh,
sorry.
that was an exponent.
No, it's not an exponent. It's just my funny way to write R. Oh, yeah. And yeah, I can see why. This is R squared. It is about the same, right?
Yeah, probably.
Yeah, no, I should learn to write more clearly. Yeah. I'll try and write more clearly. So this R with really curly on it. I don't know why. Probably comes from my days when I was doing script when I was younger. Okay, so we can now answer our question. So if we started with at R1, so we go go from R1 to R2. What is delta K? What's the change in the kinetic energy? So it's just going to be the difference in potential energy. And so delta K is going to be mu of R2 and 1. And I think there's a minus sign because energy is conserved. This is going to be Gm 1 over R1 minus 1 over 2. Let's put the minus sign on this side. Now we've got cool with these minus there. Then it'll look like that. And you can usually get the sign right by thinking about it. So if you're moving further out, it's going to lose kinetic energy. So the way to think about that, actually, I can start drawing a picture of how to think about this. So where is this here? What does this function look like? So this is R. So it looks like this, right? Where this is 0. And I could put energy somewhere on this plot, like the total energy is the sum of potential plus kinetic. So what if I put total energy here? And I could start here and then say, well, this energy, kinetic energy is the sum of potential plus kinetic. So if I start here, this is the kinetic energy is actually this distance. Because remember, E is K plus U. So I can calculate if I'm at this radius, this would be the kinetic energy. Then as I go further out, there's the kinetic energy. And the potential, as R goes to infinity, the potential energy goes to 0. So it's like really far away, you don't notice that mass of the planet. And so the total energy would then be equal to the kinetic energy at large radii. And this type of energy lets the particle go to infinity. So this is, we call this a free, it can escape. So if I'm on the surface of a planet or something and I give it a big velocity, I can ask, how big a velocity do I need to let it escape? And the answer is, if I'm at this radius, I need to have this amount of energy. So energy is 0. It can still just barely reach infinity. It's just a very small velocity. So that tells me the escape velocity. What if I have energy down here? So this is a free particle. This is one that can escape just barely. What if I'm down here? Anybody want to say what that would mean? So the ones that are down below here, they can't get, there's no way, the maximum, I can have large kinetic energy if I let it go to really small radii, but total energy is less, there's never enough to escape. So those are bound. So we'll start to see, we're going to make a lot of plots that look like this, where you put down the potential energy function, and then you draw a line, and that's the total energy. And then based on that line, you decide, is that particle bound or free or just barely able to escape? And you could write down more complicated potential functions like this. And you can leave a particle down here. These are bound to this part of the potential function. That's a stable equilibrium, but unstable equilibrium, but it can get to this part where it can get out there. you could have different, these would be called potential energy wells, where you could have bound particles. And then maybe you could have a particle that would escape. So you can think about what the possibilities are if you draw potential energy functions. Which regions allow it to, and what energies allow it to escape from which areas by drawing those pictures. So, so this is what the gravitational attraction looks like, and that's gravity. So it's pretty straightforward to now go to electrostatic potential energy. So electrostatic potential energy. So first again, we can start with the force. So the force, so I have two particles. One has a charge Q1 and the other one has a charge Q2. And they're separated by some vector, one or two. The electrostatic force looks like this, where this is a vacuum energy number. Q1, Q2 over R squared. So electrostatic force looks just like gravitational force, except that we have positive and negative charges, and gravity only has one sign for that, so it can't be negative. So when you have one is positive and one is negative, it's attractive force. So then it looks just like gravity. But when you have both of them negative or both of them positive, then you get a repulsion force. So yeah. Again, this we can integrate this because it's a radial force. So the potential energy function depends just on the distance between the two particles. And then this is the electrostatic vacuum dielectric constant thing. Q1, Q2, Q2. So did I get the sign right? So if one of them is positive and one of them is negative, then U is negative. So this has got the right sign. And so if one of them is positive and one of them is negative, then we have the same picture that we had before, like this, where potential energy goes down to negative infinity. And we can think about bound and free if we want. And we can compute the kinetic energy different. So one last picture and then we're done. What does this picture look like if we have a repulsion? If we have a repulsion, like and I can ask things like, what if I send them approaching each other? And then here's their energy. I can ask what's their minimum distance apart. Because it would be set by where the kinetic energy goes to zero. It would go in and bounce back out. Don't have enough energy to get closer together. So that's what the potential energy curve looks like for electrostatic. Okay, so I think we're done. Any questions for people who are still around? Otherwise, people who are around, I'll see you guys outside for office hours. Any questions from the online group? Otherwise, I'll just say goodbye. Bye.